So let's go. There is something you rely on every second of your existence. Something so constant, so woven into every thought you've ever had that you've never once stopped to question whether it's real. Time. The thing that gets you to work. The thing that ages your face and fills your memories and tells you that yesterday is behind you and tomorrow is ahead. The thing that, according to the deepest mathematical frameworks humanity has ever built, may not actually exist at all. These are 10 facts about time that are genuinely, structurally, keep you up at night terrifying. Not because they're speculative, because they're true. Number 10, your present moment belongs only to you. Start with something you've never doubted. Right now, as you watch this, there is a moment called now, a single shared instant in which you exist. The chair you're sitting in exists, the sun exists, distant galaxies exist, all of it happening simultaneously in the same cosmic present tense. That assumption is mathematically false. It has been false since 1905. Einstein's theory of special relativity didn't just change how scientists think about physics, it demolished the idea of a universal clock. What it established instead is that your now is personal. It belongs to you, to your location, to your velocity through space. Change any of those things and your now shifts, not metaphorically, physically. A thought experiment called the Andromeda paradox makes this concrete in a way that's hard to shake. Two people are standing on a street in the same city. One is perfectly still. One is walking slowly, maybe 5 kilometers per hour, heading toward a coffee shop. That tiny difference in velocity across a distance of 2.5 million light years to the Andromeda galaxy means their nows in Andromeda are separated by days or weeks. For the person standing still, a hypothetical alien council in Andromeda hasn't yet voted on whether to launch a fleet toward Earth. For the person walking toward the coffee shop, that vote happened 3 weeks ago. The fleet is already moving. Both of these are physically correct, simultaneously, at the same moment on the same street. What this implies about reality is the part that doesn't let go. If the now is different for every observer, then the past, present, and future aren't an unfolding sequence. They're all equally real, equally permanent, laid out like coordinates on a map that already exists. Physicists call this the block universe. Your birth is a fixed point in it. So is this moment. So is your death. All of them existing simultaneously, with what we call the present being nothing more than your subjective position moving through a structure that is entirely static and complete. The flow of time you feel, the sense that life is unfolding, that is your brain moving through a universe that has already happened. Number 9, gravity is pulling on your clock right now. Most people understand gravity as the thing that keeps you from floating off the surface of the Earth. That's correct, but it's incomplete. Gravity doesn't just act on mass, it acts on time. And it's acting on yours at this exact moment with measurable precision. General relativity describes space and time not as two separate things, but as one interwoven fabric. Mass bends that fabric. The heavier the object, the deeper the bend. And the deeper the bend, the slower time runs for anything sitting inside it. The Earth is massive. It bends the space-time around it. Which means the closer you are to the Earth's core, the slower your time moves relative to someone farther away. Your feet right now are aging more slowly than your head. Not significantly. Not enough to ever notice. But it is happening. And it is real. And it has been confirmed repeatedly with atomic clocks precise enough to measure the difference. The satellites that make up the GPS system orbit at roughly 20,000 kilometers above Earth. Up there, gravity is weaker and time runs faster for them than it does for the receivers on the ground. The difference is approximately 38 microseconds per day. That sounds negligible until you understand that 38 microseconds of accumulated error translates to positioning errors of around 10 kilometers. Engineers have to program those satellites to deliberately slow their clocks down to compensate. If they didn't, GPS navigation would be useless within hours. The satellite network that tells you where to turn is only functional because engineers constantly account for the fact that time moves at different rates depending on where you are in the gravitational landscape of the planet. Scale this up. Every star, every planet, every black hole in the universe is ticking at its own rate, some dramatically slower than others. There is no universal clock. The cosmos is a cacophony of different time rates running simultaneously, completely out of sync with each other. And you are being dragged through time at a rate dictated by the mass of the planet you happen to be standing on. Number 8. Moving faster makes your clock run slower. Gravity isn't the only force warping your experience of time. Velocity does it too. And the relationship between them is one of the strangest trades the universe enforces on everything that moves through it. The speed of light is approximately 300,000 kilometers per second. It is the absolute limit the universe places on how fast anything can travel. No exceptions, no workarounds. And because that limit is absolute, the universe has to bend other things to enforce it. One of those things is time. The faster an object moves through space, the slower it moves through time. This is called velocity-based time dilation, and it has been experimentally verified hundreds of times. Atomic clocks placed on aircraft and flown around the world come back measurably behind synchronized clocks left on the ground. The difference is tiny at airplane speeds, but it's there. The math predicts it precisely. The experiments confirm it every time. Now scale the speed up. Say you board a spacecraft capable of traveling at 99% of the speed of light, and you head toward a star 4 light years away. The round trip takes about 8 years from the perspective of someone watching from Earth. They live 8 years. They age 8 years. When you land back on the planet, they are 8 years older than when you left. But for you, traveling at that velocity, time slowed to a crawl. You experience the entire journey in a matter of months. You step off the ship a few months older to find a world that has aged nearly a decade. You haven't hallucinated the future. You have actually traveled through time, into it specifically, and you can never go back. This is not science fiction. It is a confirmed feature of the physical universe. Time travel to the future is real and already happening at every scale. Every airplane passenger, every Formula One driver, every object in motion is moving through time at a slightly different rate than everything at rest. The faster you go, the more of the world's history passes while yours slows. You can outrun time. You cannot reverse it. Number 7. You have never seen the present. Look at your hand. You believe you're seeing it as it is right now. You aren't. The light reflecting off your hand takes a measurable amount of time to travel to your eyes and be processed by your visual cortex. You are seeing your hand as it was fractions of a nanosecond ago. That gap is too small to matter in daily life, but the principle it represents scales to something considerably more disturbing. Light travels fast, but it has a speed, roughly 300,000 kilometers per second. Over large distances, that travel time adds up. The moon is 384,000 kilometers away. The light you see from it is 1.3 seconds old. Jupiter, at its closest to Earth, is about 588 million kilometers away. You're seeing it as it looked between 33 and 50 minutes ago. The sun is 8 minutes and 20 seconds in your past. Every time you look at it, you're watching a star as it existed before most people have finished their morning coffee. And this isn't just an inconvenience, it has real consequences. If the sun were to instantaneously cease to exist right now, you would have no way of knowing. You would stand outside, feel the warmth on your skin, watch normal daylight. For 8 full minutes, everything would appear completely ordinary. Then the light would stop arriving. Then, at that same moment, the gravitational tether holding the Earth in its orbit would also vanish, since gravity also propagates at the speed of light. The planet would not just go dark, it would drift. 8 minutes of perfect ignorance before the end becomes undeniable. Now look up at the night sky. The stars you're seeing aren't a snapshot of the current universe. They're a collage of different moments in history stitched together into a single view. The nearest star beyond our sun is over 4 light years away. You're seeing it as it was 4 years ago. Some of the stars visible to the naked eye are thousands of light years away. The light arriving at your eyes from them left its source before Rome had an empire. Certain nebulae we study and photograph in detail may have already been destroyed, blown apart by supernovae, that happened thousands of years ago. We're still watching the before. The after hasn't arrived yet. You have never seen the universe as it currently is. Every observation is historical. The present state of the cosmos is permanently, structurally invisible to you. Number 6. Ancient starlight is already a kind of death. This follows from the last point, but it goes further. When you look at the night sky on a clear night away from city lights, what you're experiencing is something no human tends to fully reckon with. You're looking at a graveyard. Many of the stars you can see with your naked eye are already dead. They burned through their fuel and exploded in violent supernovae millions of years ago. Their final moments of existence are already history. But the light from those final moments hasn't finished crossing the distance to Earth yet. So when you look at what appears to be a living, burning star, you may be watching the last gasp of something that collapsed while our ancestors were still evolving. The pillars of creation in the Eagle Nebula are one of the most photographed structures in astronomy. James Webb and Hubble have both produced extraordinary images of them. Tall, sculpted columns of gas and dust where new stars form, hauntingly beautiful. And based on models of how the region has evolved, some astronomers estimate there's a reasonable chance a supernova has already blasted those pillars apart. The light from that event won't reach us for another 1,000 years. Every image we take of the pillars of creation may be a photograph of something that no longer exists. This goes in both directions. If a civilization in the Andromeda galaxy has a telescope powerful enough to resolve Earth's surface and they're using it right now, they aren't seeing our cities. They aren't seeing our satellites or highways or any sign of technological life. The light arriving at their instruments left Earth 2.5 million years ago. They're watching early hominids making stone tools on the African plains. The evidence of our existence hasn't reached them yet. We're not invisible to them, we're just early. The night sky isn't a window onto the current universe. It's a set of time capsules from different eras arriving simultaneously, making the present look like a coherent picture when it isn't one at all. Number 5, black holes stop time from the outside and end it from within. If gravity slows time, a black hole is the extreme case. These are objects where mass has been compressed so completely that the resulting gravity makes the surrounding space-time behave in ways that nothing in ordinary experience prepares you for. At the edge of a black hole, at the boundary called the event horizon, the escape velocity equals the speed of light. Nothing moves faster than light, so nothing that crosses that line comes back. Not particles, not information, not time, as anything outside it would understand it. Watch an astronaut fall toward a black hole from a safe distance, and something deeply strange unfolds. As they get closer to the event horizon, the increasing gravity slows their time relative to yours. They appear to fall more and more slowly. The light bouncing off them loses energy fighting the gravitational field, stretching toward longer wavelengths, turning from white to yellow to orange to red to a deep infrared that fades below the threshold of detection. From where you're standing, they never cross the event horizon. They slow to a halt, growing dimmer, redder, fading into invisibility. Frozen on the threshold of a boundary they will never visibly cross. From inside their experience, nothing dramatic happens at the event horizon itself. Their clock runs normally. They cross it without fanfare and fall toward the singularity. If they look back out at the universe while they're falling, the opposite effect takes hold. The light coming in from outside is blue shifted, sped up. In the moments before the singularity ends them, they would theoretically watch an enormous span of the universe's future history flash past in compressed fast forward. Two different time streams, one frozen, one accelerated, both happening simultaneously in the same physical event. Black holes don't just crush matter, they sever objects from the rest of the universe's timeline. To fall into one is to stop being part of the same story as everything else. And here's what makes this more than theoretical. Supermassive black holes sit at the centers of most galaxies, including ours. The one in the middle of the Milky Way has a mass roughly 4 million times that of the Sun. Its gravitational influence shapes the timekeeping of everything in its vicinity. The universe is full of these objects, each one bending and tearing and redirecting the flow of time in its surrounding space. Time is not uniform across the cosmos, not even close. Now, before we get to number 4, if this is the kind of content that makes you want to keep going, take a second right now and subscribe to the channel. Hit the notification bell too, because these videos drop regularly and the algorithm will not always show them to you without it. If you've made it this far into a video about the actual architecture of time, you're exactly the person this channel exists for. The button is right there. Now, number 4. Number 4. Entropy is why time only goes one way. Take the laws of physics. Most of them work identically whether time runs forward or backward. Drop a ball, it falls. Run the math in reverse, a ball rises. Shine light on a surface, it reflects. Reverse the equations, nothing breaks. The physics doesn't care which direction time flows. So why does time only ever go forward? Why does a glass shatter when it falls but never spontaneously reassemble? Why does cream mix into coffee and never separate itself back out? Why do we remember yesterday but not tomorrow? The answer is entropy. And it's both elegant and deeply unsettling. Entropy is the measure of disorder in a system. The second law of thermodynamics states that in any isolated system, entropy either stays constant or increases. It never decreases on its own. Order decays into disorder. Heat flows from hot to cold until everything is the same temperature. Complex structures break apart. Energy disperses. The universe moves irreversibly and relentlessly, from organized to disorganized. The early universe was in a state of extraordinarily low entropy. The Big Bang produced a highly ordered, concentrated condition from which everything we can see has been unspooling for 13.8 billion years. That unspooling is the arrow of time. The direction in which entropy increases is the direction in which time flows. We remember the past because it left records in physical systems. We cannot remember the future because entropy moves in one direction and information only accumulates in the direction it's already traveled. Here's where this gets genuinely frightening. Entropy always wins. Every heartbeat you take, every star that burns, every thought your brain processes increases the total disorder of the universe. The endpoint of this process is called heat death. All stars burn out. All black holes eventually evaporate through a process called Hawking radiation. All matter decays. The universe expands until every region of it is at the same temperature, which will be almost absolute zero. In that final state, there is no energy differential, no work can be done, no information can be processed, nothing changes. And without change, time ceases to have any meaning at all. The only reason time exists as a concept is because the universe is still in the process of falling from order to disorder. Time is the sound a cosmos makes while it's dying, slowly, over trillions of years, but dying all the same. Number 3, in the early universe, time ran 5 times slower. We assume a second is a second. That a unit of time today is the same as a unit of time was a billion years ago, or 12 billion years ago, or right after the Big Bang. That's an intuitive assumption. It's also wrong. In 2023, researchers at the University of Sydney published findings based on detailed observations of quasars, the blazingly bright cores of early galaxies powered by supermassive black holes consuming enormous amounts of matter. Because quasars are extraordinarily distant, the light arriving from them was emitted when the universe was very young. And because the universe has been expanding since the Big Bang, that light has been stretched during its journey, a phenomenon called cosmological redshift. The redshift doesn't just change the color of the light, it stretches the temporal fluctuations of the quasar too. When researchers looked at how these ancient quasars flickered and pulsed compared to quasars close to us today, they found that the ancient ones appeared to be moving approximately 5 times more slowly. Not because they were actually slower, because time itself in the early universe was flowing at a fraction of the rate it flows now. Think about what that means. If you could have been standing in the early universe, your clock would have ticked normally to you. But looking at the present-day universe from that vantage point, we would have appeared to be in rapid fast forward, 5 times faster than normal. Time is not a fixed background against which the universe operates. It is a feature of the universe that evolves along with the universe's size and structure. As space expands, the relationship between different eras of cosmic history becomes increasingly distorted. We are separated from the Big Bang not just by distance, not just by the 13.8 billion years on a calendar, but by a qualitative difference in the nature of time itself. The universe back then was running on a fundamentally different clock than the one governing your experience right now. And the universe is still expanding, still changing, which means the rate at which time flows is not necessarily finished evolving either. Number two, below the Planck scale, time probably breaks down entirely. You can divide a meter into a centimeter into a millimeter into a micrometer. You can keep subdividing distance into smaller and smaller units, and at each step, the laws of physics you're used to keep working. The same is generally true for time. Seconds into milliseconds, into microseconds, into nanoseconds, smaller and smaller intervals, but the physics remains consistent until you reach the Planck scale. The Planck time is approximately 5.4 times 10 to the power of negative 44 seconds. This is the smallest interval of time that current physics can meaningfully discuss. It's the duration it takes light to cross a single Planck length, which is the smallest meaningful unit of distance. These numbers are so small they have no intuitive comparison. They sit at the boundary of everything our equations can describe. Below that boundary, something goes wrong. The two frameworks that dominate modern physics, general relativity, which governs the very large, and quantum mechanics, which governs the very small, are incompatible with each other. They describe reality using completely different mathematical structures. For most purposes, this incompatibility doesn't matter because the two regimes don't overlap. But at the Planck scale, they're both relevant simultaneously. And when you try to combine them to ask what happens at time intervals smaller than the Planck time, the math doesn't produce answers. It produces infinities. It produces nonsense. At this scale, space-time is thought to become what physicists call quantum foam, a chaotic, bubbling, fluctuating structure where the smooth, continuous fabric of space and time you experience breaks apart into something probabilistic and undefined. At this level, the distinction between before and after loses meaning. Cause and effect stop applying in any reliable way. Tiny structures called wormholes may be opening and closing spontaneously across intervals too small to measure. The terrifying implication is that time, the thing that feels most fundamental to your existence, is not fundamental at all. The orderly progression of moments you experience every second of your life is an emergent property, something that only appears smooth and linear because you are far too large and far too slow to perceive the chaotic substrate beneath it. At the deepest level of reality, there may be no time, just a probabilistic storm of quantum events from which time arises like foam on the surface of an ocean. Number 1. Physics doesn't actually know what time is. All of the previous entries describe things that time does, how it bends under gravity, slows with velocity, flows in only one direction, breaks down at the smallest scales. What none of them address is what time actually is. Because here's the thing. Despite centuries of measurement and mathematics, despite atomic clocks accurate to within a second over billions of years, despite theories that can predict gravitational time dilation to parts per trillion, physics does not have an answer to that question. In the 1960s, theoretical physicists John Wheeler and Bryce DeWitt attempted to combine general relativity and quantum mechanics into a single unified framework. The result was the Wheeler-DeWitt equation, a mathematically coherent description of the quantum state of the entire universe. The equation worked. The math held together. But something was missing from it, conspicuously, structurally absent: the variable for time. In the most comprehensive unified equation physicists had ever constructed, time simply wasn't there. It dropped out of the formulation entirely. This is called the problem of time in quantum gravity, and it hasn't been solved. When you try to describe the fundamental nature of reality at the level where quantum mechanics and gravity both apply, you find a picture in which time is not a required ingredient. The universe, at its deepest mathematical description, appears to be timeless. Approaches like loop quantum gravity describe the universe as a network of interconnected loops. The relationships between these loops define the geometry of space. But no time variable appears in the fundamental equations. Time, in these frameworks, is something that emerges from the collective behavior of the system, the same way temperature emerges from the collective motion of molecules. A single molecule doesn't have a temperature. Temperature is a statistical description of a large number of molecules together. Physicist Carlo Rovelli argues that time is the same kind of thing. Individual quantum events don't have a time. Time emerges from the vast statistical complexity of many quantum systems interacting, perceived by observers who are themselves embedded in that complexity. If this is correct, then time is not a feature of the universe. It is a feature of how certain sufficiently complex systems experience the universe. The smooth, urgent, unstoppable flow of moments you feel right now, the thing that makes you feel late, makes you grieve the past, feel anxious about the future, is not a property of the cosmos. It is a property of you. Of the particular way a biological mind embedded in a large, complex thermodynamic system makes sense of its surroundings. The universe beneath all of it may be completely still, timeless, static, and the sensation of time passing, of moments arriving and receding, of life being lived, may be something your brain generates as a translation mechanism, a biological story it tells to make a fundamentally atemporal reality navigable. Everything you've ever felt, every memory, every loss, every anticipation, every moment that seemed to matter, all of it may be your mind's way of moving through a universe that has no concept of now, no arrow, no clock. A universe in which the question of what time is doesn't have an answer because the question assumes something that was never actually there. That's where the list ends, not with a solution. With an open problem sitting at the center of the most successful physical theories humanity has ever built: time. We know how it behaves, we know how to measure it, we know how to use it to navigate satellites, to calculate the age of stars, to predict the orbits of planets with extraordinary precision. We don't know what it is. And the deeper the physics goes, the less certain it becomes that it's there at all.